Gravity is one of the most basic forces in the universe, yet it's also the least understood. We know that all objects with mass exert a gravitational force on every other object with mass. And we have a pretty good idea of how that force depends on the masses of the objects and the distance between them. But why do they attract each other? What's the origin of this force? Where does it come from? We have a good idea for how the other three fundamental forces arise. They're all generated by the exchange of particles. The electromagnetic force is carried by photons, the strong nuclear force by gluons, and the weak nuclear force by the W and Z bosons. But gravity is different. It seems to have no carrier. Indeed, the hypothetical particle that would carry the gravitational force has turned out to be unobservable because it is either too heavy or doesn't exist. The problem is that if you want to describe gravity in terms of an exchange of particles, you need some new physics, and physicists haven't found any evidence for new particles. This situation has led to a lot of speculation. Some people claim that there are no such particles because gravity isn't a real force, but an illusion. However, most physicists disagree because they can see no way out of the conflict between Einstein's theory of general relativity and quantum mechanics. The most straightforward way to resolve the conflict is to quantize gravity, which requires a particle. But if this particle exists, it must be extremely light. This is why there has been so much excitement about recent claims of fifth forces that supposedly appear at low energies. These could in principle be the graviton or another particle that couples very weakly to ordinary matter. But unfortunately, these experiments were inconclusive and later proved to be incorrect. However, there's another way to explain the origin of gravity without postulating new particles. It was first proposed more than 50 years ago by the physicist John Archibald Wheeler. He suggested that the gravitational interaction arises from the exchange of information. Unfortunately, Wheeler's idea hasn't attracted much attention until now because it seemed to make no testable predictions that could be verified or falsified. That's why it was often dismissed as a kind of philosophy. However, in a recent paper, two physicists have shown that Wheeler's idea has surprising consequences that can indeed be tested. Let's have a look. According to Wheeler, what really happens when you throw a ball up in the air is that the ball and the earth exchange information. To be precise, they exchange what's called entropy. Whenever two systems exchange information, their entropies change in opposite directions. If you have a closed system with high entropy, like a hot cup of coffee, then you open it up and let the coffee cool down. Both the coffee and the environment become more ordered. The total entropy has decreased. According to Wheeler's idea, this means that the two systems have exchanged information about their states. More specifically, they have exchanged information about how much energy they have. In the case of the ball and the Earth, the ball has more potential energy per unit mass than the Earth. So the Earth gains information about the possible states of the ball, which is why its entropy increases. For the ball, the situation is different. It loses potential energy and gains kinetic energy. This makes it less informative about its own states, so its entropy decreases. In essence, Wheeler's idea is that the gravitational interaction is mediated by information. Information is conserved, but it's distributed differently between the interacting objects. The interesting thing about this idea is that it makes a prediction for the sign of the gravitational constant. You see, in Wheeler's approach, the gravitational interaction is an entropic force. It arises because systems tend to move toward states with higher entropy. But an entropic force is always an attractive force. This is why Wheeler's idea can't explain why antimatter doesn't stick together. And indeed, if you look at the mathematics, you find that the gravitational constant g must be positive. At first sight, this might seem like a minor issue. After all, g is a constant of nature that just pops up in Einstein's theory of general relativity. It could just as well be negative. But in fact, the issue is much deeper. You see, there are many ways to quantize gravity. All these theories have something in common. They postulate a particle-like excitation of space-time called a graviton, but they differ in how exactly this graviton behaves. In particular, they differ in whether the graviton is described by a boson or a fermion. The easiest way to see the difference is to look at the spin of the particles. Bosons can have any spin, but they must have integer spin. Fermions must have half-integer spin. The difference is important because it determines how many of these particles can occupy the same state. For bosons, there's no limit. All graviton theories predict this because they require the existence of a graviton with spin 2. This is why they recalled spin 2 gravitons. If you look at the equivalence principle, which says that the gravitational pull of an object doesn't depend on what it's made of, then you can try to infer the spin of the graviton. Indeed, physicists have done this, and they found that it must be 2. But if you look at the mathematics of spin 2, you find that you can't make sense of a negative gravitational constant. Therefore, all these theories predict that gravity is attractive. There have been attempts to get around this by changing the statistics of the graviton. You see, there's nothing in Einstein's theory that requires the graviton to be a boson. One could, for example, try to make it a fermion. Then the gravitational constant could be negative, but that wouldn't make much sense because it would mean that matter would fly apart. There have also been attempts to introduce a third type of statistics that would allow for both negative values of g and repulsion and attraction. But the problem with these ideas is that they require modifications of Einstein's theory that are incompatible with observations. Wheeler's idea, on the other hand, doesn't require any modification of general relativity. It's simply an interpretation of the theory, and it makes a definite prediction for the sign of g. So why hasn't anyone noticed this before? The reason is that the prediction of Wheeler's theory is correct only if you consider a system with a large number of degrees of freedom. Only then does the entropy term dominate and determine the sign of g with a small number of degrees of freedom. You can't tell whether g is positive or negative. This is why the authors of the recent paper say that Wheeler's idea has so far not been testable. They go on to point out that this changes if you have systems with a large number of interacting particles, such as those in condensed matter systems. These systems have a lot of entropy, so Wheeler's argument should apply. And indeed, the authors of the paper have calculated what this means for the equation of state of certain strongly interacting systems. This gives rise to an additional contribution to the pressure which can be measured. And that's what makes this an interesting paper. It's not that it explains where the gravitational constant comes from. For that, we'd need to know how the entropy of a system is related to its mass. This relation isn't known, but it's likely to be universal and the same for all types of matter. So it shouldn't depend on the details of the microscopic structure. This means that the correction to the pressure that they calculate should apply to all fluids, and it will be particularly large for those with strong interactions. So this is a prediction that can in principle be tested. It'll be interesting to see whether the experiments will confirm Wheeler's idea. But even if they don't, the paper is still interesting because it shows that the idea isn't as obscure as it might look at first sight. I hope you enjoyed this video. If you did, maybe you also enjoy my science news videos. They're very much science news. You'll find them on a website. Thanks for watching. See you next time.